Welcome back, everyone, to the La Space Academy, Level 1, Session 9. We've got a lot to cover with you tonight, and we have an amazing speaker. As you can probably see in the participant list, we're joined by Sherry. She's back from LPSC, and perhaps at the end of our session during the after show, maybe Sherry will share a little bit of her LPSC experience with us. But before we do that, Sherry, how are you doing?
Doing well, and in fact, I'm looking really forward to Jessica's talk today. Hi, Jessica. I see you online, and we have the pleasure of having the Lucy systems engineer broadcasting from the East Coast. You're at Goddard, right? Right, Jessica. We'll let you catch everyone up in terms of where you are and maybe some of the cool things that you're working on in terms of where Lucy is today. But we have a very special presentation tonight. We want to bring you, the behind the scenes kinds of ideas in terms of how missions come together, and Jessica has a wonderful presentation. So we have a few things that we'll do housekeeping at the end, but we want to just be able to give Jessica as much time as she would like to share with you some of the exciting things that she does in her everyday job. So I want to know, does your job come with a cape? Because I think most of the people working on missions are super people most of the time. So anyway, with that, why don't we go ahead and go right into the great presentation we have for you. There we go.
Jessica, you're on. Welcome.
Thank you. Can you guys hear me all right?
Certainly can.
Great. Thanks for having me, and I'm certainly excited. I don't know if Sherry and Dan have shared with everyone that we are hosting some L-Space engineers this summer on the Lucy project, and so we're really excited. I'm going to have 2 folks in my office. We'll have a couple folks at the principal investigator's office, as well as several folks out at the spacecraft office in Lockheed Martin, Denver. So glad you guys could all join me tonight, and hopefully the talk will give you some information on what we're doing on Lucy, where we are today, and hopefully that'll give you some idea of whether or not you like the idea of becoming a systems engineer. So I have a presentation for you, and Dan, I'm not sure if you want me to just queue it up and share my screen, or if you guys have it.
That would be great. If you could just click share and share your PowerPoint, that would be perfect.
Mm-hmm. All right.
We can see your screen.
Great.
And just play slideshow and you're good to go.
Awesome. Thank you.
Thank you.
Okay, so as Sherry said, I'm the project systems engineer for Lucy. And most people want to know, well, how the heck did you get that role? I started out at Salisbury University, bachelor's in physics, and really trained on the job in engineering. So I'm coming up on 17 years this summer for working with NASA. And I spent my first 7 years at Wallops in Virginia. And I have been at Goddard for the last 9 years doing systems engineering. So it's been really exciting. So what do I do? You can see me there pushing the strong back on a SpaceX Falcon 1 rocket. That was one of my early missions. When I worked for Wallops, we had a payload that was an experiment to fly on the Falcon 1. And so I spent 3 weeks out in the Marshall Islands living there and essentially preparing to launch this science payload. And so even though I work, a normal 8-hour day, 5 days a week, we definitely have field work and lots of it as we get closer to launches. So it can be a lot of fun. But I essentially lead teams of engineers to help build satellites. And I'll show you some of those pictures. But first, I just want to give a quick overview. What is systems engineering? So systems engineering is looking at the big picture. So looking across mechanical, thermal, electrical engineering and making technical decisions on that big picture. We are always cognizant of what are the performance requirements that we need to meet in order to get the science that we desire, and how does that hardware work in the given environment. So for Lucy, you'll see We're going to the Trojan asteroids that are in Jupiter's orbit. They're 60 degrees in front of Jupiter and behind Jupiter. And so you can imagine the environment there is quite different than if you were an Earth orbiting satellite. So we need to not only show that we can meet the performance needed, for example, taking images with cameras and what's your signal to noise ratio and what's your resolution of your camera. Not only do those performance requirements matter, but so do the environmental requirements. Can you survive the launch on the launch vehicle? Can you survive the Jupiter radiation environment? Those types of things. The systems engineer is looking at all of those across the system. So I just thought I'd show you what systems engineering looked like in 1958 and what it looks like today. This was a team that I worked on in 2015 called MMS, the Magnetospheric Multiscale Mission. And so systems engineering has really evolved, and I'm super proud to be a part of it. So here are a number of missions that have been launched over the years at Goddard, and I've highlighted 3 of them here. MMS that I just mentioned, Lucy that you see in the bottom, and that's the current mission that I'm working on, and then also LDCM. And today I'm just going to talk to you about 2 of those missions to give you a sense of what the different phases of the mission look like. So if you look along the bottom of the screen, you'll see there's pre-phase A, which is where you're basically drawing on a napkin, putting together a proposal to go ask for dollars and look to get your research funded. And that moves all the way from pre-phase A into phases A and B. Phase B, you see the arrow. Lucy's been approved beyond phase B. We're actually now just in the beginning of phase C. Phase B was basically the formulation of all of our requirements, putting together a preliminary design, showing that that will in fact meet the needs of the mission. And now, as we've been confirmed, which is essentially a gate that headquarters reviews what we've been doing so far, and they give us the authority to proceed forward into phase C, which is basically your cutting metal stage. Your final design is coming together, you are releasing drawings, you are mocking up harnessing, you are putting together engineering test boards that aren't necessarily the flight build, but it's the precursor that actually shows that you can in fact demonstrate performance can be met with that technology. So that's where Lucy sits today. And so at the time that I pulled this together, I was talking about phase B. So I'm going to go through a couple charts to show you what phase B looked like, and then a few more charts to show you what a phase C and phase D start to look like. So for Lucy, I'm sure you guys have heard from other speakers on Lucy, but just as a refresher, our principal investigator is working to understand how did the solar system form. And you see the little video here, hopefully it's playing on your screen, that the planets, there are several different theories as to how the planets came to be in their current locations. And so part of Lucy visiting the Jupiter asteroids, those asteroids were scattered, as you saw in the video, and landed in the Lagrange points, which are around Jupiter. And so by going and investigating those objects, that will be able to tell us, where did those objects originate? Was it inside the solar system or outside the solar system coming in? And so by looking at the diversity of those objects, the size of them, the mass density, the spectra of those objects, we'll be able to understand where they came from in the formation of the solar system. So here are the Lucy targets. And you'll notice that the top row is objects in the Lagrange point 4. Lagrange point 4 has 4 objects that we plan to visit. The first one we'll visit in August 2027 called Eurybates, and we all have a lot of fun trying to pronounce these names at work. Nobody pronounces them the same, but we have Eurybates, which is a spectral type C, and you'll notice that the different objects have different spectral types. So you'll see Ptolemy is a very small object, and it's a P-type object. And Lucas and Oris are both D-type objects, and you'll notice that we're visiting those 4 objects over several months. So from August 2027 to November 2028, we'll fly by each of these objects, image them with a series of different cameras in the thermal infrared, in panchromatic bands, in near infrared, and many different wavelengths to make sure that we understand the properties of each of those objects. The bottom 2 objects at Lagrange point 5 are Patroclus and Menecius. Those 2 look very similar in size, and it turns out that they are believed to be a binary pair. So they are in fact orbiting one another, and as we approach them, we'll need to look at one object and then swing our instrument pointing platform to look at the other object. And so we'll do a lot of swinging back and forth to look at both of those. And that's kind of a difficult problem for systems engineering, because not only do you need to know where the objects are to find them, centroid on them, and then switch between them, but you also need to make sure that you're not smearing the images that you're taking and that you're still meeting the resolution requirements of your camera. So that's just something to think about from a systems engineering standpoint. So here's our trajectory. We are visiting 6 Trojans, as you just saw in the previous chart. We're also visiting a main belt asteroid called Donald Johanson. And I'll just pause here to say, I don't know if folks have already heard from Hal or Kathy, our principal investigators, on the naming of these, but Donald Johanson was the gentleman who found the Lucy hominin skeleton in Ethiopia, of which this mission's named after. The hominin skeleton, just like it's taught us so much about how humankind formed, Lucy will tell us so much about how the solar system formed. And so that's why we're called Lucy. And the first object that we visit in the main belt asteroids is named after the finder of the Lucy skeleton, Donald Johanson. And when we visit Donald Johanson, we're going to use that as a rehearsal. So we're going to test as much of our spacecraft and as many of our instruments as we can when we visit that object. So I'll show you the trajectory here. Following the red dot, Lucy's leaving Earth, and we swing around in a 1-year orbit that puts us into an Earth gravity assist. That Earth gravity assist pushes us out, and it's about 2 years. Oh, I'm sorry, there's your 1-year orbit. And then the next one is about 2 years. I think I pushed the button in the wrong direction. Give me a second. Okay, so the first year, you go into the orbit, you come around, you come by the Earth and do an Earth gravity assist, and then you go by Donald Johanson. And so this is where we'll do that rehearsal and check out everything that we can possibly check out. And this is a great time. We can calibrate instruments, we can look at this asteroid. Now we are flying by this asteroid twice as fast as all of the other asteroids, so that poses a challenge. We aren't setting out to meet any of our science requirements here, but we're going to do our best effort to learn what we can about our system, and if there are any course corrections that we need to make, this is a great opportunity for us to learn. So when you leave Donald Johanson, it takes a while to get to the L4, and you see the 4 asteroids here at L4, Eurybates and Ptolemy, then Lucas and Oris are all observed. That looks like it went by pretty fast, but if you remember the previous chart, it takes months to hit each of these objects. The shortest time between 2 objects is the first 2. Eurybates and Ptolemy are 34 days apart. So those are our closest objects. And so we have to think about what could we learn at the first object that we could turn around in 34 days and execute some sort of change, maybe change to the resolution of a camera. And what could we change in that short amount of time and not invalidate all of our previous testing and previous processes. So then once we leave Oris, we come back in and do another Earth gravity assist. And it looks like we might be able to see Donald Johanson again, but that's not actually the case. The Earth gravity assist then kicks us out towards the Lagrange point 5, and you see the objects coming into view there is Patroclus and Menecius, the binary pair. And we actually don't come to those two objects until 2033. So definitely keep an eye on us over the years, because we've got lots of great science that's going to continue to provide good information about the solar system and the formation of it. So I'm pretty excited that this mission is going to go on for quite a while. Similar to the New Horizons Pluto mission, we've learned a lot over the years, and it took 9 years before they even reached the object. So that was pretty interesting, certainly a long-term investment. Okay, so systems engineering. There is a lot involved in making sure that we understand our requirements, that they're organized in a way that we can find them, that they're flowed down to all of the hardware appropriately. So this particular flow diagram, you'll notice on the far left, there are different levels, one through 4. Level 1 is headquarters, approving our requirements. What are the science objectives that we want to achieve? What images will we want to collect in the case of Lucy? So for example, Lucy needs to get a scan of each of the asteroids across the terminator. The terminator is the division between the day and the night side of each of these asteroids. And so LTES, being a thermal infrared imager, will look for that signature as it scans across each asteroid and try to determine where they switch from the day side to the night side. And so that's the type of science requirement that would be up at level 1. Well, in order to get that particular instrument to satisfy that requirement, the requirements need to come through the mission requirements document. And you heard me say earlier, we worry about the environment as well. So both of those documents are circled at level 2, where we're worried that first we have to meet the performance to get that measurement of the day-night side terminator scan. But we also need to make sure that that instrument survives the environment that it's in while it's doing its job. And so the mission requirements document and the environmental requirements document flow straight down, and you'll note they go to all the different elements there. And so you'll see on the right-hand side, I don't know if you folks can see my mouse or not, but you'll see there is a packet of instrument requirements there, one for LRALPH, one for LTES, and one for LLORI. Those are our 3 instruments. And so those requirements that come from headquarters and are approved by headquarters flow all the way down to those instruments. And so there's lots of different requirements in this hierarchy, but that's just to give you a flavor of how one set of requirements flows down. And systems engineering is always worrying about that, because not only are we setting the requirements, but we are going, as hardware is being built and tested, we are looking backwards at how each piece is verified. So for example, for the LTES camera, there would be some performance testing to show that they can in fact meet their resolution requirements. And not only that, meet their resolution requirements in the right environment. So there might be a thermal vacuum test where they're in a thermal vacuum chamber and they need to, again, prove out that they can meet their signal to noise ratio without thermal distortion impacting them. And so those tests then get checked off by systems engineering to say, okay, they met the requirements of that test, they had a successful test with no errors, and then we go and record it against the requirements to show that that verification was actually met. So here's some other example driving requirements for Lucy. These are pretty straightforward. We have a 21-day launch window that starts October 16th of 2021. So please watch us, because between October 16th and November 4th, hopefully we will have launched. We've got all the way up until 21 days in that period. But usually if things go well, we usually launch on the first day. It might be a couple days, you never know. Could be weather in Florida in October. We have a total wet mass of 1435 kilograms. That's what our launch vehicle can carry. And therefore we cannot exceed that when we add up all of our dry mass, which is all of our hardware, as well as our fuel included in that number. So all the fuel that we need to push that spacecraft around that trajectory that I showed you, the fuel plus the structure mass needs to be less than the 1435 number, or the launch vehicle can't carry us. We also need to survive for 11.6 years. As you saw, we launch in 2021, but we don't hit our last object until 2033. We also have requirements to be single fault tolerant, and that basically means that we can't have a single point of failure. And if we do have single points of failure, so a place where if something broke, it would be mission ending, we can't tolerate those types of failures. Now, if you've got parallel strings on something and you have a redundant component, now you're protected so that if one fails, the other one can continue to do the mission and you're not dead in the water. We also need to be able to survive without ground contact for 28 days. Because we're going so far out and a lot of our operations are happening autonomously, we need to be able to continue to be in a safe thermal and power state on the spacecraft while we're not in ground contact, while we're not talking to it. We also, you see here, we have our fuel requirements. We have a bipropellant and a monopropellant system on board serving different functions for the mission. And so you see here, we've got our delta V margin. So in meters per second, how far we need, how we need to move the spacecraft around in that particular orbit. And this dictates the budget that we need maximum, plus some margin on top of it for things like if we have to do collision avoidance maneuvers. Say there's an object in the sky that we didn't anticipate was there. Usually we get those orbital predictions ahead of time. There is a group of folks that do watch for orbital debris. And so you get those notifications and you plan for small maneuvers to avoid different objects that are out there in the solar system. And so we have contingency margin available for things like that. Okay, so here's our payload and spacecraft. And so in the upper right is the spacecraft, and you see there are two large solar array wings here. Kind of look like one of those Chinese fans, and that's basically how they open when we launch. They will open up and snap into place, essentially. It's a little more complicated than that, but just at a high level, that's how they fan out and open. In the front here, you see the high gain antenna for communications, and we also use it for radio science. We take Doppler measurements with the Deep Space Network on the ground, and that is what provides our mass density numbers for each of those Trojan asteroids. And that's actually calculated and reconstructed on the ground after the mission. We won't know the mass right away as we're flying by. And then you'll see the structure, spacecraft structure behind that high gain antenna. And that's carrying, there's a couple of decks there that carry all of the hardware. So for example, the command and data handling system, all the different propulsion components, the propulsion tanks are back here. On the top here, on the top deck, you see the instrument pointing platform, and the close-up of that is on the far left. So the far left, you see our different instruments. We have the LORRI camera, and you can see the names here, Long Range Reconnaissance Imager. And you can also see the wavelengths at the bottom here that I mentioned earlier. I don't know if the little icons are covering that, but there's a wavelength in nanometers at the bottom. So you can see that some of the instruments do overlap in wavelength, but some are, for example, the MVIC, it has panchromatic as well as color, even though it's the same wavelength there. And we've got the LISA instrument, the LTES instrument. And if you look here, we also have two terminal tracking cameras. So terminal tracking cameras are really interesting on this mission. These cameras help us to centroid on the object. So basically, as we're coming up to each of the asteroids, our navigation team will let us know when we're pretty far away. So roughly 60 days before reaching the target, we'll be fairly far away. And the navigation team will be able to tell us where the object is within a 75-kilometer uncertainty. But once we get inside that time frame, the next 4 days or so of the mission, we rely on these terminal tracking cameras to actually locate the object, centroid on it, and feed that position of the object back into the software or state estimation software that's on board to help us to continue to stay tracking right on that object, keeping all of these other cameras pointed on it so that they can take their measurements with the right performance. So I'm going into a lot of detail here on the preliminary design. I hope that that gives you a flavor of the types of things that we actually need to present in order to get our design past that gate and to start to cut metal. So I'll show you a couple more photos, but this is the level of the design. You can tell it's fairly detailed. This is the Lucy spacecraft inside of a fairing, a launch vehicle fairing. And so you're looking for clearances. This little yellow circle shows you that that high gain antenna is pretty close to the edge of the fairing of the launch vehicle. And so we talked about environment. We want to make sure that when we shake this spacecraft to the launch loads that we expect from that launch vehicle, that we, number one, can survive, but also number two, that we don't contact the inside of the vehicle with a high gain antenna, because that could certainly pose a problem for our communication downstream. So here are some more pictures. I'm not going to go into this detail. I just want you to see that we have to worry about overlapping fields of view, making sure that cameras are aligned to one another where they need to be. So there's a lot of systems engineering that goes on here to make sure that as you're moving the instrument pointing platform, that each of these cameras is still able to see the Trojan target, and that they're able to, the travel of the gimbal on that instrument pointing platform doesn't preclude them from seeing the target any longer. So here's just an idea of when we're taking science. So I started talking about at encounter minus 60 days. So 60 days before we hit the first Trojan asteroid, we are starting to use our LORRI camera to do optical navigation and to search for any satellites around those asteroids. And LORRI continues to stay on and take measurements up through 20 days after we've left the object. So we're following the object, and as we go by, we are still continuing to look back on that object. We send a ground-based knowledge update at 4 days before we are at closest approach to the target. We're using those terminal tracking cameras, as I stated before, to walk us in and keep us pointed on the target. And those are really only used 4 hours around our closest approach to each object. And then the Ralph cameras are looking from encounter minus 12 days to encounter plus 20 days. And then that thermal infrared thermal spectrometer is looking only for 2 days around the closest approach of each object. So that gives you hopefully some sense of when those instruments are taking images and how they're working independently but in parallel to take the Lucy science. And here's just a sample of our power budget. And if you look at this, I won't go again into too much detail. Certainly, if you guys want to take a look or have questions, let me know and we can talk offline. But the power performance at the Ptolemaic encounter turns out to be our driving case. And so we're looking at what activities are going on. So cat bed heaters, for example, on the far left, those come on to prime the propulsion system. So you're warming up your thrusters with the cat bed heaters. You're doing desaturations of your reaction wheels. So you're spinning, you're dumping that momentum off of the vehicle. So different things are happening here that are taking up different amounts of power, and you need to balance all of this. The terminal tracking camera comes on and starts imaging here, so you see different bumps in the curve. Then the spacecraft actually pitches over when we're really near close approach. So this scale at the bottom here is time from close approach in hours. And when we get close to the vehicle, close to the Trojan, as I was saying, we're watching it, and then we're essentially pitching or flipping over to turn around and watch the object as we're going away from it. And so that's what this deep dive here is in the power. We actually flip over and the solar arrays can't see the sun for a period of time, and we need to charge back up as we come back on the sun. So these are the types of systems engineering problems that we worry about when you put the whole thing together and you're going to operate it a certain way. To meet your science requirements, you have to do these things operationally, but you have to make sure that you're still power positive, that you're thermally safe, things aren't getting too hot, or in this case for Lucy, too cold, because we're very far away from the sun. We're at about 5.7 AU at our farthest target. So that's that's pretty far. It's much different than if we were, say, going to Venus, and we'd be pretty close to the sun, and you know, charging solar arrays probably wouldn't be such a problem. So you saw on those pictures, we had those huge, you know, I joke and call them Mickey Mouse ears, but we had those huge solar arrays. They're about 7.2 meters in diameter each. And that's, again, to make sure that we've got enough power and we're able to charge our system to hit each of these encounters and support all the hardware that's on the spacecraft. So here's types of products that systems engineers are responsible for. In addition to those types of analyses, we also have to worry about our mass. And when we went into our preliminary design review, PDR, we were showing about 14.4% mass margin, which gave us roughly 109 kilograms to work with in later phases should we run into problems. But I will tell you that since PDR, which was in late September, we are now in almost April. We have since grown the structure considerably. Our harness has come in and has grown something like 25 kilograms above what's shown here. Our structure grew by 34 kilograms, and our propulsion system grew by 6 kilograms. So hopefully you're feeling as shocked as I have been for the last couple months, because that is a serious amount of growth. And so we are now worrying, it's actually an issue on our mission, we're worrying about mass, and we're going back to everyone and saying, look, how can you save mass? Can you lightweight something? Is there something we can cut? Is your estimate of high fidelity, or is it really more of a WAG? And so we're really going back and scrubbing and trying to figure out where can we shave down mass, and how can we ensure that we will not exceed the amount of mass that the launch vehicle can throw. And so, you know, that also involves giving up some fuel, perhaps. So we have to be really careful, but we also have to make sure we have enough mass. That's our currency in the systems engineering world. Enough mass to actually solve problems down the line. And I'll show you some of those problems in a couple minutes here. So here's another product for systems engineering. And hopefully by now you're still interested in systems engineering. There is a lot of paperwork involved, but there's also a lot of really cool testing and a lot of fun problems to solve. So I'll get to those in a second. But our risk database is the tool that the systems engineer uses to essentially communicate out to our project management, to our lead scientists, what's going on, what are we worried about, and what are we doing about it. So you'll see here we've got a matrix. What's the likelihood and consequence of this risk going forward? So for example, the first one, and I'll just pick this one and I'll leave the rest for you to think about, centroiding and diverse shaped targets. So I showed you those objects. That is our best approximation of the shapes of the asteroids. We are doing ground-based observations. So we've got telescopes on the ground. We actually have volunteered campaigns. We have a Slack website. So I think there's an opportunity if you wanted to actually volunteer and come out to one of our ground observations. You help out by running a telescope and taking data on each of these objects. And basically as the object is occulted in the sky, that gives us some information about the shape of the object. So we are continuing to learn, and we will continue to learn until we launch, and even beyond our launch, we'll learn about these objects. But if we don't totally know the shape of the object, then how can we plan around the uncertainty of that object? If it looks like a potato, okay, fine. But what if it, you know, has all kinds of, I don't know, morphed shapes, and maybe it looks like a potato with a head on it. I have no idea. You guys can use your imagination. But these shapes, we know them to a certain degree, but we need to know them even better. And the more that we know them and the lower the uncertainty, the better off we'll be in terms of making sure that we can centroid on those objects with that terminal tracking camera I showed you. So that's a top risk for us. And the likelihood of us being sensitive to the shape is certainly, it's not 0, it's ranked as a 2, and I can send you guys some of the criteria on how exactly we weight these. But the consequence we have listed here is a 4. So a 2 by 4, you see the number 1 on the chart over here, makes it a yellow risk. Certainly having red risks is it's encouraged to find them, and then as they're red, you want to spend a lot more time on the red ones to mitigate those and get those damped out so that you have a robust system going forward. The yellow ones are just as important. The green ones are also important, but there may be opportunities in there where you can accept some of the risk, and we call that a residual risk. And so there may be a place where you can accept going forward that we're going to carry this risk and we're not going to do anything about it. So that this helps you to make decisions and rank things based on the criticality of them. And so that just hopefully gives you a flavor of how a systems engineer uses this tool to make decisions. So going forward into CDR, which our CDR, Critical Design Review, is this coming October. So we are gearing up at this point, and we're in the middle of burning down some of our concerns, our watch items and risks. We are working on our concept of operations, and we're working on our fault protection details. Fault protection is all about, if something goes wrong, how do we recover the spacecraft? How do we recover the instruments? So a lot of detail and thought is being put into that area right now. And then we have different systems analyses. I showed you the power balance. We're also worried about MMOD, that's micrometeoroid orbital debris. So we're worried about other stuff in the atmosphere touching or slamming into the Lucy spacecraft. How do we protect ourselves from that? Well, maybe we use some mass to cover a certain section, like cover a harness that might be susceptible to getting hit by micrometeoroid debris. So that's where hopefully you're seeing the theme here. It's tying back to systems engineers' currency is mass. Well, mass can be used to solve a problem by shielding this harness so that it won't get hit by this debris, but that also doesn't afford me that mass to solve problems later on down the road. So I have to pick and choose based on the risk and the criticality of that item. Okay, so I'm going to jump into phases C and D, and this is building the hardware and testing the hardware. This is my favorite time in a mission. Absolutely love it. Other people are more comfortable in the analysis and the preliminary design world, but this is what I love. The last mission that I did, Magnetospheric Multi-Scale Mission, MMS, was a cluster of 4 satellites that you see here. And this colorful picture is actually showing you the Earth here with its magnetic field lines, and the sun over here. The solar wind is pushing up against the Earth's magnetic field lines. I don't know that it's really that color, but it illustrates that in this region here, something's going on with the plasma and the electrons and the ions between the solar wind and how it interacts with the magnetosphere here on the Earth. And so, science aside, the engineering part of this is all about progressing to building the hardware. So you see the quad chart here. We started out really in that very, very early pre-phase A drawing. I mean, it looks like something you draw on a napkin, to a more detailed design. So this is your PDR design here in the upper right corner, as you saw on the Lucy spacecraft as well. It's very detailed. And then phase C, you start pulling it together and putting all the hardware on. And so you see the guys in the clean room in their bunny suits working on the spacecraft. We had a stack of 4 on this one, which was particularly cool. I was not the lead systems engineer on this one, but I was in charge of MMS number 4, which is the top one on the stack. So that was pretty fun. And here's just some more sketches of how that observatory was laid out. And so you can see it is a fairly complicated assembly. We had to start out by populating the instrument deck separately with the different instruments. We worked on the propulsion thrust tube separately. And when it was time, the solar arrays went around the center of that thrust tube. We also worked independently on the spacecraft deck and put on the components there, like the battery and the command and data handling system, the transponder, things like that. And you see the propulsion module with the tanks supported on these various panels. And so integration and testing is all about how are you going to organize yourself to put it together well. If there's a problem, can you take it apart easily, or does the team need to spend lots of time going backwards to take something apart that failed a test? And so we tried to make it very modular in this way. And if you remember back to the Lucy spacecraft, that's also fairly modular, having those 3 different decks. So if you needed to, you can work in parallel, one deck over here, another deck in another portion of the clean room. And so you'll see some of those photos coming up here. So I talked about field of view on Lucy. You can see how complicated on MMS the field of view was. Each one of these instruments needed its own field of view, represented by the different colors on the right-hand side. Lots of overlap. There were lots of complaints. I can't see, this other instrument's blocking me. You know, people say it's a lot like herding cats, and it really is, because in this particular mission, you had 25 different types of instruments, and they all needed to play nice together. And that's the systems engineer's job, is to make sure that they can play nice together and meet their mission requirements. But here's an image of one of the decks before anything was populated on it. And you can see we've got our photographer taking pictures. She takes pictures all along the way during all the hardware builds. It's awesome. It's a great resource because you can go back and look at those images to figure out, was something broken when we put it on? Did you notice it? What configuration was it in? Was it upside down? Was it backwards? Was it in the wrong spot? Who knows? She takes very detailed photos of absolutely everything all along the way, every single step. So it's pretty neat. Here is a mock-up of our spacecraft, and this is in an anechoic chamber. So this is one of the tests that we did before we put our antennas on the spacecraft. We needed to understand, how are the antennas going to respond if there's interference from signals bouncing off of the thermal blankets that are covering the deck of the spacecraft? So we used aluminum foil and a wooden mock-up to put together one of the decks of the spacecraft. And you see there's a boom in the middle here, an axial double probe boom that we had that we also worried might reflect signals from the radio frequency transponder. We thought that it might bounce those signals off and then in fact take away some of the signal that is being transmitted back to Earth. So we were worried that we wouldn't get all our data down to the ground if the signal is corrupted by this. So we wanted to test it in a anechoic chamber. You can see all of these little cones here. They basically absorb the radio frequency information. And so you're basically what amounts to in a soundproof or very quiet room from the perspective of radio frequency. And so then you can get a signature of what your antenna sees just based on the spacecraft interfering with it. So I don't know if you guys can hear this video or not, but what you're seeing here is one of our antennas going through a vibration test. The vibration test is measuring or representative of the launch loads that the launch vehicle will put on the hardware. And so every piece of hardware needs to prove that it can survive the launch environment. So you see this thing vibrating, it's going through a sinusoidal vibration test to prove that it can survive the launch. And if you watch closely, I encourage you to watch the bottom radiating element, the bottom gold element here as we go forward. And you couldn't hear it, but certainly there was cursing involved. We test and test at every level of assembly. We do it at the component level that you just saw for that antenna. We do it at the full up spacecraft level, as you see in these photos. And we even do it at the stack level in this particular case, because we were stacking the spacecraft on top of one another and needed to separate them. And so to separate them, that causes a small shock event as they separate from one another, and you fire a pyro device to move the two observatories or spacecraft away from one another when it's time to deploy them. So we test in the same manner that we would fly. We want to test the way that the environment that the spacecraft would see from its point of view. So you saw the vibration test as if we were on the launch vehicle and getting ready to lift off. The shock tests here in the upper left case are all about when you separate those vehicles from one another. There's a thermal balance test and a thermal vacuum test. Those occur to show that you can survive the hot and cold plateaus or the hot and cold swings of the environment that you're going to see. So you first have to understand your environment in order to lay out what the test needs to be. And then you want to add some margin on top of that. So if you thought that based on the environment that you're going to fly in, that your spacecraft would see minus 60 degrees Celsius up to plus 100 degrees Celsius, then you need to create an environment in the thermal vacuum chamber that mimics that. And then you need to go a little bit beyond that by 10 degrees Celsius in each direction to show that you have enough margin for any uncertainty in the way that you model that environment. So these are the types of things systems engineering really worries about. Make sure that we do in fact have margin and we're covered. We didn't just design straight to the capability that we have and we can't go beyond that. So hopefully you can hear this. This was us stacking 4 spacecraft in the clean room. And obviously this is a time lapse, but it's over a 2-day period. And it's certainly a team effort working on these satellites. So hopefully that gets you guys as excited as it does me. It was really fun to be in the clean room for those several days as we were stacking all 4 of these. And then once we were done with the stacking, we actually, you see there's a door right behind here, this large gray door. We rolled that up. Well, actually, I'll take that back. We put the blanketing, the MLI shielding down on this, draped it on these observatories to keep them clean. We rolled the door up and rolled this out to the vibration cell and did a vibration test over several days that proved that the entire stack, fully assembled in flight configuration, can survive the launch. So similar to how you saw that single antenna, if you look closely here, and it's kind of hard to tell because there are red tag covers on all of these, but those antennas are mounted on here in different locations. Red tag covers basically mean remove before flight. So these covers are there to protect things. When we go to do the vibration test, the covers come off. It all has to be flight-like. These silver panels are covering the solar arrays. They're protecting them. Those are essentially red tag covers as well, even though they weren't colored red in this particular configuration. So, and then of course there's the most exciting part when you're enveloped inside the launch vehicle fairing and you're launching. Here's that launch environment I've talked about several times. And at some point here, you'll see the fairing or nose cone will open up. And actually, first you're seeing first stage separation on the rocket. There's your fairing separation. Here are your 4 spacecraft. You can see all the different instrument apertures here. See one of those antennas on the top. This is MMS 4 separating, followed by 3, 2, and 1. And then the remaining stage of the launch vehicle fell away. And then we start opening booms. And MMS had quite a number of booms. We had 8 booms. These 2 are magnetometer booms. They had magnetometers on the end of them. We had single pole double probes that are coming out on the sides here. There's 4 of those. And then we had 2 axial booms, one on top and one below, that are identical. And those were looking at electric fields. And the single pole double probe, I believe, we're looking at magnetic fields. So we were measuring what's going on with the magnetic fields, the electric fields, what were the ions doing between the solar wind coming off the sun and the Earth's magnetic field. And to really get a good picture of that, we had to fly all 4 of these in formation. So you can see all 4 of them coming into view in this particular video. And so, you know, thinking back to Lucy, you know, there are operational constraints that we have to think about in terms of how we want to fly these to get our science data. And it's no different on MMS. It's only different based on the type of science that we want to gather. And so as that launch was occurring, I told you guys I was in charge of observatory number 4, MMS number 4. I'm looking at the data coming back. You know, we're launching on the screen over here. Our mission systems engineer is extremely excited. We also had, you know, plenty of political figures in the room, one of which, the center director at Goddard, was over my shoulder waiting because I was going to be the first one to receive telemetry. So it can be nerve-wracking at times, but it's so exciting. Launch fever is the best feeling in the world. This is an onboard video of the MMS number 1 separating from the last stage of the launch vehicle. So this camera is actually on the launch vehicle, but this is one of our actual satellites leaving the vehicle. Okay, so last thing I want to leave you guys with, my motivation for working at NASA. Daniel Pink actually wrote a book, and in his book, he talked about what motivates people, and it's really not money. Certainly there's the aspect of if you can't eat or don't have a place to live, that's one world of, you know, dealing with money. But in terms of loving your job, if you're comfortable enough, you've got your home, you've got your food, in my mind, I look for autonomy, mastery, and purpose, as well as teaming. So autonomy, basically the freedom to be able to influence folks, work with a team and influence them, but also the freedom to have a flexible work schedule, the freedom to, I don't want to say be your own boss, because I certainly have a boss too, but the freedom to be trusted to do your job. Mastery, certainly mastering a skill, mastering engineering, math, physics, science, whatever it is that you're interested in. Being able to master something can be very fulfilling. Just working on, you know, a project at home can be very fulfilling when you complete it. So being able to master something is what I look for in motivating myself. Purpose, you know, with each of these missions, I told you before, Lucy is all about understanding how did the solar system form. To me, that is a higher purpose. That is a really interesting purpose that interests me. So I encourage you guys, find your purpose in your career. What about that gets you up in the morning? And then team. I am an extroverted person, as you might be able to tell. I like to work in teams. Some people prefer to work individually. Every person's different. Every person's motivation is different. But these are some of the things that motivate me. I like to work with groups of individuals. You saw all those folks in the clean room moving those spacecraft around. You know, you saw tens of people in a team getting something done, orchestrating that in such a way that it's efficient and we're still having fun at the same time. So those are the types of things that motivate me. Certainly I encourage you guys to think about what motivates you. I'm excited because we have a whole bunch of interns coming in this year. Hopefully you guys will think about interning with us in the near future, because Lucy is going to start moving into that phase C where you're going to start to see hardware in the clean room. We're just starting to get there now, now that we've moved out of phase B and into phase C. And so internships, in my opinion, will become more and more exciting coming to Lucy over the next year. So thanks, and I certainly am looking forward to your questions for me.
Thank you so much, Jessica. That was great. And we do have a Q&A session going on here. I'm about to post the opportunity for the students to post questions.
Thanks, Jessica. That was really great. You know, it reminds me all the time how many moving parts there are on a mission. and looking at some of the tables and watching the chat in terms of someone were saying like, that's the most awesome job. And others like, it would stress me out so much. I don't know if I could take it. And, but the real winner for me shot was watching you watch the separation of that deck and deploy, and just knowing, you know, you lived that, you were part of that. It's almost like birthing something, you know, in terms of seeing that actually deploy and do what it needs to do. And just orchestrating, and systems engineering is one of the things that we hear the most of teams needing, or looking for new talent coming their way, in terms of people that will have that big picture view. And, you know, you've given a great overview in terms of what it's like to live and breathe in, you know, systems engineering. And so we thank you very much for that. That was really great. And your talk about risk, I mean, you all are going to have risk matrices in your PDRs. And Dan, don't we have some of that put together in terms of some helps?
We do.
Okay, and so we'll be making sure that you see that, and we'll get that up to the top of everybody's viewpoint. But anyway, I saw a lot of great questions coming through the chat, and we told them to make sure that you come over here and put them back into the Q&A. And you're welcome to, you know, take pictures that you see, or I can throw them at you, whatever you'd like to do. So they're kind of scrolling by here.
Sure. Yeah, so there's a question about difference between a systems engineer and a project manager. Project managers really do spend a lot more of their time looking at the overall schedule. They're looking at the cost. As we're going through those risks, for example, it is a joint role where we work together very closely. If I say, hey, I've got this red risk or this yellow risk, and I really need to spend some money to fix this problem, I need to talk to my project manager and get his authorization that the project's willing to spend dollars to do that. And to so the project manager is really worried more on the cost and schedule side. They certainly care about the technical, but they're also trusting the lead systems engineer to guide them on the level of the risk.
Okay, and what does a normal day look like for you? I mean, it's probably depending on which phase you're in and where things are, you know, launched, build, whatever you're doing. What do you do in kind of your day-to-day normal time?
Yeah, so right now, as we're heading into our next review in October, we're doing a lot of mini peer reviews or tabletop reviews where we're going to lay schematics out on the table, and we're going to have folks from outside come in and scrutinize the work that we're doing. So right now I've been spending days sitting in a review and looking over the design and making sure that we're able to answer all the questions the independent reviewers have for us. I'm also going down to the machine shop and walking around and taking a look at some of our hardware is in fact being machined. And so checking in with the guys on the floor, how's it going? You know, are we still on track? A lot of times with the resources that we have at Goddard, sometimes the answer is, oh no, this other project is now in front of you. You know, they had higher priority, so you're kicked to the back of the line. Well, hold on, let me go get my project manager, and we're going to talk about who's got the highest priority in the queue. So the day can range from sitting at my desk and working paperwork all day to running around to a little bit of both. So it's very fluid. I'm answering the phone all the time. You know, when you're the lead systems engineer, more than anything, it's fighting fires. The phone will ring and someone will say, I've got this problem or I've got this concern. And one of the best things that I've learned from all of my mentors that I can do is to be as open as possible so that people will come talk to me and tell me their concerns. Because, you know, folks, you probably remember Columbia accident. You know, there are different examples in engineering history where people at different levels were not heard. And so it's really my job to make sure everybody across the project can come to me with their engineering concern, their worry, and I will listen to them, I will hear them, and I will make sure that I'm thinking about the problem at hand and either doing something about it or understanding why, working with them, why I think it's not a big problem. But you know, it's all about communication and me being open. And so that's why my day is fluid. I'm answering the phone and I'm trying to get people to tell me what's going on, you know, what's worrying you, and not making them feel like I'm going to start running around and waving a red flag or placing blame, things like that. So teaming is a really important aspect. And being a leader and communicating, I spend a lot of my day doing that. Sometimes I joke and say that this job is 80% social work and 20% technical. So.
That's well put. And I appreciate even just, talking about the mass growth that you've had in terms of Lucy. I mean, having all of the things come in and making sure all those puzzle pieces fit and you end up being what you need to be on the launch pad to where you can actually optimize the mission. That is a lot, again, of things that you have to make sure is happening and go back and negotiate and do all the things you've been doing. So somebody was asking, in terms of going from systems engineer, the mission launches, what do you do afterwards? You were looking at telemetry. What kinds of things do you do as as it's actually in cruise or heading to its destination?
Mm-hmm. Great question. Typically, the systems engineering team will stay on board up through what's called commissioning. So basically, as for the example of MMS there, as those booms are coming out, that takes a couple of weeks to deploy all of those booms. We're looking at the health and safety of the entire system. We are, as I said, commissioning, which basically means we are turning on the instruments, we're checking them out, we're making sure that the temperatures are right on them, we're looking at the spacecraft bus to make sure that we have the right power profile, that things are running as we expected and as we saw them on the ground during our environmental testing and during our performance testing. And so a lot of that time is spent with the same engineers who've been working with the hardware, watching it on orbit and making sure that things are as we expect. And then as problems arise, you get called in. Even now, MMS launched in 2015. So 4 years later, I'm still getting the emails. I don't sit on console on a daily basis, but if there's a big problem, sometimes I'll get called and they'll ask me to come in and help them solve a problem. And that's pretty exciting too. So that sort of adds to continuity in following the mission, even when you've transitioned off to start another mission. So I stayed with MMS for about 6 months while they were in the air and in orbit. And then I moved over and started doing other work on other missions.
Well, there's a couple questions about becoming a systems engineer. I mean, how does it differ in terms of, say, studying aerospace?
Oh, so, quite honestly, you can start in a background, any engineering or many different science fields. So for example, my degree is in physics. It's actually not in engineering, although I did minor in microelectronics. You can be an aerospace engineer, you can be a physicist, you can be electronics engineer, mechanical engineer, it doesn't really matter. Many of those different disciplines start out doing smaller portions of a project, and then you build and grow over time until if you decide you want to get into systems engineering, then you go and try out on the job looking at different disciplines. So for example, I started out doing electronics in our guidance, navigation, and control branch at Wallops. So when you saw me at the very beginning, I was pushing that strong back on the SpaceX vehicle. I was working on sensors at that point. I was wiring up harnesses and testing sensors like different IMUs and different accelerometers and different ultrasonic sensors, different things like that. I was testing sensors. I was testing out GPS units, just starting really small. And then over time in my career, I realized that, I really like the big picture. And so I talked to my boss, and there are plenty of on-the-job growth opportunities. So I just investigated different areas. They let me go work on a cryogenic mission because I knew nothing about cryogenics and thermal engineering. I said, guys, I don't know anything about thermal engineering. Can I learn? And so I'd go over there and I'd spend 6 months working on a project and shadowing a thermal engineer and learning about it. So systems engineering, one way to think about it is there's a wide breadth of information, but you're not extremely deep in any one area. So you're paying attention to the big picture, cross-cutting, but you're not necessarily going down to the resistor level on every electronics board, or you're not going down, deep into every screw on the structure. So a lot of times folks will start in an engineering background of one type, and then expand to learn a shallower depth in the other disciplines, and that helps you become a better systems engineer.
So there's another question Maria has that says, how do you keep the science team and engineering team working cohesively?
Oh, that's a great question. So we definitely have team meetings where scientists are invited. And so those are actually kind of my favorite meetings, where the science team and the systems team starts talking about how are we going to actually fly this mission. So we spend lots of time, we call them concept of operations meetings. And the scientists will come and join us, and they'll ask us all these questions. Well, I don't understand how the spacecraft, how does the spacecraft work to get me what I need? And so we actually, we have to be careful, because the scientists, and you have to love them. I mean, I have my physics background, so I can't say anything negative about a scientist, but they will ask you for the moon, and you have to push back and say, well, hold on, that's outside the scope of our requirements. That sounds like a desirement to me. I know that would be nice to have, but we have to consider the cost cap that we're in, and we can't spend more dollars for all these extra things. We have to do only what we set out to do. And if there's, room later on down the road when we're done with the job, then fine, maybe we can think about it. But in general, we have to keep them at bay quite a bit.
Kind of like we want more shiny ornaments on the Christmas tree.
That's right. Exactly.
Somebody was asking, what kind of software would be best to know if you want to be a system engineer? Is there anything in particular?
Oh boy, so we write in a lot of different languages.
Such
Certainly C, C++, VML. Let's see, certainly MATLAB is good to have a background in MATLAB, because we do a lot of analysis using MATLAB.
How about Python?
Yep, Python. Some of our guys still write in Fortran, which is ancient.
Wow.
Obviously, we're moving on from that as we continue developing. But no, honestly, there is some flexibility in the software that we use, depending on what it's for. So there isn't any one specific language. I would say, gravitate to the one you like to use, and certainly if there's opportunity to grow and learn other languages, do that as well. But it's just like the market in other things, other technologies, it's always evolving.
Yeah, I noticed the 2 interns that you picked for your group for the summer had very long software lists. They were pretty versed in a lot of different languages. That was pretty cool. How much CAD, or do you use CAD at all? If there is, what kind of CAD do you use?
Yeah, we do. We use CAD for mechanical engineering. CAD is used all the time. We also use Cinda and Fluent for thermal engineering, and so there's a lot of exchange of models between the mechanical engineers and the thermal engineers. They are constantly going back and forth, making sure that if the mechanical engineer is moving a box from this location to that location, the thermal engineer has to be happy with that, because you're moving big masses around, and so you're changing the thermal dynamics on the structure.
Selson wants to know, in terms of additive manufacturing, is that evolving to try and save mass and things within the spacecraft systems, or is this something that's still kind of out there?
I mean, there's certainly the idea of light weighting and scalloping on structures and things like that. There's certainly consideration given to that. What's difficult in mechanical engineering, especially for a mechanical analyst, is as you start essentially cutting holes in things to lightweight or using different materials. Now you have to model all of those scalloped edges that you cut away, or all of those holes that you put in the deck. You now have to model that, and it's really a lot of extra work to model all of those details in a CAD model and then get an accurate representation of the finite element model and show that it's still meeting margins when you apply the different launch loads to it. So there's a lot of ideas out there, but it's also a lot more extra work to analyze as you start using those techniques.
So there's another question that says, how do you handle the stress or the frustration when you expect a result and you don't get it?
That's a good question. Managing expectations is certainly part of the job. I have to manage other folks' expectations, and so a lot of times as a risk comes up or a problem comes up, we try not to make promises too early. We try not to state anything but the facts as we know them and as we're learning them, and state what our plan forward is, and not necessarily put out hopes or expectations that we have. We try to keep it a little more factual in the engineering world. Certainly there are times where I think something's going to go one way and it doesn't, and it goes sideways on me. Truthfully, I try not to let it bother me. It's not a personal thing. It's if you look at it a little more as just engineering and it's not personal, then it's pretty easy to kind of separate that out and say, oh, well, okay, that happened. Now we need to take a new path. Let's think about what are the steps we could take to go forward. Sometimes it can be exciting as well to see something react totally different than what you expected. And it can be a fun challenge to get the engineers together around the table and say, okay, well, that stumped us. How are we gonna fix this? And there are some engineers that are just so creative and so interested in that, and they see that as a challenge and they love that stuff. So sometimes things going sideways on you can actually be kind of fun if you look at it that way.
Well, and somebody had asked about, I'm getting a lot of feedback suddenly, Dan. I don't know what's going on here. Just a minute.
Oh, nobody else is unmuted. I'm not sure.
Okay, is this better?
Yeah.
Okay, so in terms of the test drive by Donald Johanson, if you have anomalies, how do you actually deal with, being able to optimize things that maybe aren't going the way you think? What's going to happen at that point?
Mm-hmm. So for Donald Johanson, since that's a rehearsal, we're just going to keep flying by it. We're not going to try to adjust anything in real time. And what we're going to do is take all that data on the ground and we're going to pore over it for the next 2 years before we hit the next object, the first science object, Eurybates. And so we've got a lot of time to sit and think about it and react to it on the ground, and perhaps replan our science sequences as we fly by these objects. So in that particular case, I think we have the benefit of time on our side to think through that.
Okay. And what about, we'll just do one last question here. I guess, we do a lot of things on well, I'll do 2 questions. We do a lot of things on teaming on LaSpace. And because we know that that's really a challenge for a lot of groups, and the number one ask we've had from our needs assessment from missions and from aerospace and whatnot is having people learn how to work on teams and optimize projects. What's your biggest challenge in terms of what you see in terms of teamwork and getting things done?
I think making sure folks are speaking the same language. I spend a lot of time sitting in meetings where one person will bring forward their opinion or bring forward their analysis, and another person will speak on that same topic, and they're talking past each other. So I spend a lot of time making sure that folks are, in fact, speaking about the same item at the in those conversations. I can't think of an example right off the top of my head, but certainly there's a lot of that going on. So, oftentimes it's a nuance. It's something small that someone says that the other person didn't catch. And so you've got to help them reconnect with one another in a team to realize what's being said and to realize how things work such that you can make a good decision going forward. So I think there's a lot of that challenge in the teaming. And someone asked how many people are on the team. The Lucy team, gosh, we've at least 200 people are on the Lucy team. I am not in charge of all of those people. In the systems engineering team, in my office, there's probably 15 of us right in my small group, and then that extends outward to the spacecraft team that's probably got over 100 people on the spacecraft team. The project management teams have dozens of folks. I mean, there's folks in very different areas all over the project, folks that worry about our contracts, folks that worry about the cost and schedule. So there's many different roles across the project, but there's several hundred people working on Lucy.
All right, and one last thing was about we saw a lot of chatter about the telescope campaign, viewing campaign. When will you be, do you know when you will be actually recruiting? I think maybe it'll be talked about at the science team meeting coming up. But in terms of some of the folks that are all over the country and far and wide, I think there's some interest there in being part of that viewing campaign if possible.
Yeah, that'd be great. So Sherry, after this, I'll get you the Slack website that people can join. But we have viewing campaigns going on. The next one is November 4th, and that happens to be in Australia.
Okay.
And then we've got
field
a couple,
trip.
Yeah, we've got a couple coming up in Africa. We've got several coming up in California. So over the next couple of years, there are multiple trips. There's a limited number of slots, and the project, I think our principal investigators do the selections on those. So I'll end up on the list, and who knows if I'll get it or not. But I at least want to go out for one of them. So I'll get you that information, and certainly we'd love to have some of the folks here participating. I think that'd be fantastic. There's really no training involved in doing that. And so if you've got the enthusiasm and the interest, I think that you'd be an excellent candidate.
All right, and we're getting our Lucy Ambassador applications honed up and ready to be going on before the end of this academy too. Well, this has been fantastic as usual. Lot of good information, and just that big picture view of all the things that are going on to get that mission to the launch pad, off the planet, and towards those Trojans. It's going to be an amazing mission in terms of the things that we're going to see for the first time, and maybe answer some really foundational questions. So thank you so much for spending your evening with us. I know you've already had a long day and you're on the East Coast, and thanks so much for just bringing us all this and spending the time for Q&A. So
anytime. Thanks, guys.
You're getting lots of thank yous in the chat, as you know. Well deserved, but thanks so much. We sure appreciate all of your information, and these guys got a really good chance to get a more of an introduction to systems engineering. Who knows? Maybe we swayed some people to go that direction. So
yes,
it'll be fun. All right. Well, thank you, and good night, and we'll be talking to you again, I'm sure, down the road. So
Thanks,
right.
Jessica.
Thanks, everybody.
I'll see you in Denver.
All right. Take care. Bye.
All right. Bye. All right, we're going to turn the corner and talk about some housekeeping things, right? And what do you think, Dan? Where should we start?
Well, we have been receiving a lot of emails about the PDR, so let's talk about that first.
Do you want to do a poll, or have you done that yet?
I have not done that yet, but I'd like to do one.
All right.
Okay, so if you joined our academy at the very beginning, you saw a question probably that I posted in the chat asking who's ready to submit their PDRs this week. So the original PDR Deadline is April 5th, but I've got a poll. I'm curious. So I'd like to ask you all to join us on Mentimeter. And I'm curious to see who would like a 1-week extension on their PDR. I see one person says no.
They probably have it all done.
Yeah, and that's 3 people. That is great.
Well, and you can get a little bonus points by handing it in, so that's not
what
a
I was going to
problem.
say. We would love to start receiving them. If you're ready to go even before the April 5th deadline,
Oh yeah,
feel free to start submitting those. Our reviewers are ready and anxiously awaiting.
we are.
Yes.
We've already been caffing up in terms of no sleep for several days in a row.
It's like training for a marathon.
Yeah. So if you don't need the extension, kudos, and we will, definitely get started, and you'll have those freshest comments compared to the marathon. So we'll go ahead and let you send them in, and that's good to know. Okay, so I guess, looking at the poll, do you think we should go ahead and give them another week?
I think so. And actually, so I'll be sending these risk charts. Garrett, before he left us, put together some really
Before
great...
he moved, he didn't leave us.
That's
he
true.
Moved.
I was just talking to him. Yeah, I was just talking to him on Tuesday. By the way, he says hi, everybody. He's enjoying Oklahoma. But before he moved, he he created this risk chart kind of template for you or guidelines for you to follow. And he actually worked with Jessica Thompson on putting them together. So I will be sending those out as well. So you can feel free to include those into your PDRs. And we are going to go ahead and honor that 1-week extension. What do you think, Sherry?
Yeah, I think we can. And again, our goal is to have everyone successful. And if you're struggling with a section, if you don't understand something, reach out. This is not a pass-fail. We want everybody to pass and pass well and own it. So this is something that, it's not added stress, but it is getting something to where you will have a document at the end as we get this matured and we get this feedback to you, and you get it scrubbed up, that you can show to future employers, you can show to internships. We've had the past academy was getting getting a NASA internship interview, and I said, send your PDR, your copy of the PDR ahead of time to your interviewer to show the caliber of the things you've done. I mean, this is a document for you. And so what you and your team are producing is extraordinary. And we've had that reaction from NASA when they've looked at these. So we want you to be successful. Don't feel like, it's not good enough. We're going to give you the feedback to help you make it good enough. So even with the week extension, if you get it done, we want it to do the job that it's meant to do, which is this is the training, the workforce development training we're helping give you practice in. Some of the students are asking, can the presentation be a PowerPoint?
Yeah, so I'm glad that was asked. So first of all, your PDR, we want it in an actual report format. So Sherry, I know you have some right next to you. Can you just kind of like thumb through one of the PDRs just so everybody gets a sense of what one looks like? I know some of you have asked for these particular PDRs to be sent to you, but these students are still working on polishing up their PDRs based on the feedback they received. Yeah. But this is what we're expecting, a document similar to this, maybe not as thick if your team is not there yet, but in terms of your PDR, so if you can submit a PDF version of your PDR, but in addition to that, so this has been shared on your project manager Trello boards, and hopefully they got this out to everybody else, the instructions on how to actually present your PDR findings. So that is what you can put into a PowerPoint presentation, very similar to what we do here on Zoom, what Jessica just did, sharing her PowerPoint with everybody here using Zoom. You and your team can actually record a presentation, and you have your free Zoom accounts have up to 40 minutes that you can record with. All we're asking is for a 10-minute presentation. It can be less than 10 minutes, but we will not accept longer than 10 minutes. So we want you guys to be very concise with your words and your ideas in your presentation. So that means, just as the document that I shared with you says, we want you to practice these, assign roles for each of the team members, who's going to be talking about what. If you feel like you need to script this out, that's absolutely fine. We've had a variety of different PDR presentations submitted to us, but those you'll record them and then you can either upload them to Google Drive, you can upload it to YouTube, and just share the link with us. So the files obviously will be too large to share, so you can just share the link with us along with your PDF of your PDR.
And I will remind you again, please follow the numbering and the outline that we gave you in terms of the PDR document, because that is exactly how we are going through and looking and rating each section. So don't make us hunt, make it plain, copy the same names and the same numbers and use that same system. That will help things go much smoother, and you will not have grumpy reviewers, which you never want to have. So, and it's not, I said pass fail, Maggie or whoever it was that was worried about that there is a grade on this. No, you don't. Your grade is how much you own it yourself in terms of understanding the process. I mean, Jessica covered a lot of things in here in terms of just all the pieces within a mission. And they're coming up on CDR, which is a critical time. They've been through preliminary design review. All these things have to be down for the reviewers to know these mission teams have this idea in hand, studied, you know, all the risks retired as identified and retired as best they can. And this is their best estimate of being able to go forward and start the build. And so you want to make sure your ideas are coming across. If there happens to be a section where it doesn't apply, just put that section down and say, does not apply. I mean, you don't want to skip numbers. You don't want to leave things out. You want to be as thorough as possible in thinking about your project. If you've got questions, send them to me. I've been answering a bunch of them. We've been posting them on the FAQs in terms of the forum. We want to give you as much, you know, feedback as you can. So work with your team. This should be a team project. Mm-hmm. If, you know, Dan and I have been meeting with people, if they have questions or questions about their team, we're here to help. So please go ahead and reach out. And again, we are trying to make this a good experience, but we are stretching you as well. You're going to know a lot more. It was fun looking through, you know, the people that were actually answering some of the questions that were coming up. And, you know, I was very impressed in terms of a lot of the knowledge that some of you are carrying already. So everyone can learn from this, and we want to make this, again, a very good learning process with a deliverable, something you'll have at the end. Okay.
And we do, so your video presentation will be due with your actual PDR. So you've received your week extension if you need it. You can submit your PDR and your video link to lspace@asu.edu. When you submit that, please. And somebody's asking, so Kayla's asking, can we submit a PowerPoint recording with audio only? So when you record in Zoom, I believe with Zoom, your video will be showing, but if each of you, your team members, maybe just want to have your profile picture. So for example, if I stop sharing my video, but I've got my profile picture uploaded, you can see my picture while I'm talking, but you can't actually see my video. I think that would be fine. But it'd be nice to see, you know, who's actually talking. Again, we also want these to be as professional as possible. So I know somebody asked about playing music in the background during their presentation. Sherry, what would you say about that?
I have not been to any PDRs that have ever had a soundtrack.
Yeah.
Just so you know.
That's what I thought you were going to say. But
so this is we're practicing for real.
Yeah.
This is not, you know, games or anything else. We're trying to professionalize you in a way that's going to get you farther up, you know, in your career pathway, and show that you have that maturity, that you've experienced things that are not normally taught in class. And so these are the things that we want you to, you know, look at ways that you can start to really practice that professionalism. This is really going to be important for you. And I think that when we finish this conversation, Dan, I want to be able to talk about the next proposal academy as well.
Yeah.
So I think we've got less than a minute. So go ahead and we'll continue in the after show. We'll get back to questions. We'll pull some more questions, but we do want to talk to you about the next academy that's going to be offered. NASA has come to us, and they are seeing a gap on the professional landscape in terms of people with good ideas, and they're throwing them out there for NASA to see, but they're not in a selectable form. People are not learning how to write really successful proposals in terms of giving your idea some credence to actually get funded to go and develop that idea. And so we are going to be running, the next academy is going to be about proposal writing for NASA, and learning the ropes on how to actually construct and put down those ideas in a way that NASA could select them. So this is going to be something that's going to be the 12 weeks long. It will be open to you. This is not something we're finding taught in universities, especially in undergrad, but for you to understand how to actually be additive to your career, having the skills to propose and be out there, being able to add to the new ideas, creation of ideas, looking at where to go look and see where those gaps are that are something that you can propose to, what an announcement of opportunity looks like, how you build a proposal, the things you need to pay attention to. We're going to be going over all of those. And as an extraordinary offer at the end of that, the team that comes up with in that session, in that academy, with the best proposal idea, NASA is going to give and fund $10,000 towards the startup of that idea. It's real money. This is a real thing. So they want you, again, it's not $10,000 to go to Target. It's $10,000 shopping spree. This is actually seed money to start your proposal, getting legs to mature it even more. So this is going to be quite an extraordinary opportunity. We are going to ask you to be all in terms of being serious about it. There's going to be a learning curve. There's going to be things you're going to be asked to write. And again, NASA will be selecting that best idea. So no, you're not going to keep your current group. No. I see Stephen.
Yeah.
We're talking with NASA. I'm meeting with them. Actually, the head person for this is coming into ASU to discuss with us what this is going to look like. And we're going to be coming up with those parameters and all the things that'll be part of that, just the rules document, basically. So we're going to be opening that academy when, Dan?
Just posted in the chat. So the Proposal Academy applications will be available April 5th on our website. You'll receive an email from the Space Academy as soon as those are available. You guys have first pick in terms of application. The seating is limited for our academy due to our limitation in Zoom. So you'll actually we're also opening this up to our current level 2 academy. So you'll be blended with that group. And we took a poll, and about, I want to say at least 180 of them are ready to go for next semester.
Yeah, so you'll want to apply early and apply quickly, because we will fill the academy. Good news is we will run it again for the next 3 sessions. We're going to be running the same Proposal Academy. We're trying this out for NASA. Let them see how this is going. But it is going to be something that you need to be serious about. And I know, let's see, where was it here that I just had a question that caught my eye.
While you look at that, I just want to let everybody know. So we are launching this in the summer. So we are starting this one in the middle of May 16th, if I'm not mistaken.
And somebody asked if this is a new academy, level 2, and Jessica answered that as well. We're now calling it the Mission Concept Academy and the Proposal Academy. So these are the 2 academies that are going to be different. We really feel like this will be more productive in terms of what will be additive to your career. And if you learn these ropes, and I've won about $50 million worth of proposals. I really enjoy proposals. It's a challenge, and doing it right is really important. So this is going to be something that we want you to actually start as an early career person, learning the ropes to where you have some utility and marketability in terms of going forward in terms of your career pathways. So, and the question that was, there it is. So Corey had asked, will there be an opportunity to continue with our current teams on furthering the ideas presented in our PDR? If it fits the roadmaps, the decadal survey, the design mission architectures, the things we're going to point you to, this can't just be an idea that you want to do right now. You've got to show where it maps to what NASA says it's needing. And so you've got to tether it to a real need right now, that they're on that. Now, the things we're talking about, characterizing the water feedstock, could very well be in there. And so in that case, Corey, that would be a yes. And we're going to work on the structure of the team. We've got to decide what that's going to be yet. We have some discussions. But we're looking for, what it is that you can do. You can use subject matter experts at your colleges or universities. You can find faculty that are working on programs that are similar and loop them in to make you more credible. This isn't going to be just students. You've got to have subject matter experts that you're going to go out and shop for as well. And we'll be talking about all those kinds of steps within the academy. So it will also be, Elizabeth, it'll be for the fall semester as well and next spring. So summer, spring, summer, fall, and spring will be the 3 that we're going to be piloting this for NASA, and we hope to continue it after that. It's up to them if they see some good work. So again, they're spending money on this. We want to make sure. It'll be missions, it'll be technology, it'll be all of that, Mariah. So we think that there'll be a lot of things that will be pretty exciting within this academy, and this is going to be very novel ways for you to learn a fantastic skill. Okay, so that's breaking news. And with that, I think
while we get ready to talk about something else, I just put up a quick Menti just out of curiosity. I'd like to participate in the Proposal Academy would you like to do summer 2019, fall 2019, or spring? Oh, sorry,
2020.
spring 2020. My bad. Sorry. So spring 2020. So while you all complete that, Sherry, a couple people asked in the chat about the budgets.
Yes, I already posted it too.
Okay.
The thing that I lose sleep over, and I told them earlier that it will be a very simple template for them to fill in. So, sleep well. You're not going to come with something that's going to be terribly complicated. I'm trying to make it to where there'll be a lot of good instructions, explaining everything, where it goes, and it's just going to be plug and play. That's my goal. So, and Rachel says there is no Academy 3, is there? No, there isn't. Only for last session's Academy 2 will there be an Academy 3, because they have not had the Proposal Academy, but we're going to allow them in. So
yeah, but we've got the Lucy Ambassador applications also that we'll be releasing soon.
Right. And Catherine and I are working on that in the Lucy team meeting. We're going to be having that up before the end of the Academy. And I don't know, Catherine, do you want to unmute and say anything in terms of
so Veronica's asking what the Lucy Ambassador program is.
Yeah, so the Lucy Ambassador program is going to be an opportunity for some of you guys to get some extra training and then go out and give kind of spread the word about what the Lucy mission is, and we'll give you all of the resources that you need, teach you about the program, give you fun toys and stuff that you can, teach people about what Lucy's all about.
That's right. And it's a great way to be the public face, basically the public facing face of Lucy, and be telling the story about Lucy. So we've got all kinds of good ideas, and it's something that NASA really enjoys having in terms of grassroots people in their local communities actually being that person that comes and helps share the ideas. So anyway, we'll be coming pretty soon with that, right, Catherine? We're going to have that formed up pretty quickly. We're well moving along on that. So, and we don't know in terms of, yeah, I'm just looking, Veronica, yeah, it'll be involved some social media and outreach, visiting schools. There'll be a whole array of things that we're going to list out in terms of the application and give you more information so you know what it's like. And So a scienteer. Yes, exactly, Maria. That's right. It's just kind of like an Imagineer. You're the scienteer, and it's going to be, it'll be it's great to tell the story of such a cool mission. So, and Jacob, no, not all of the internships have been offered yet. We were actually making some calls today, weren't we, Dan?
We certainly were.
So not everybody has heard quite yet. We have some very happy people that
Well,
did get the call.
Yeah, before we actually say anything about the Lucy interns, I do want to give a shout out to Jenna Connolly. I don't know if she's still in the room, but Jenna emailed me. Yes, she is. Jenna emailed me a while ago to notify me that she received a NASA internship. So congratulations, Jenna. That is great. For the rest of you that have applied for NASA internships, aside from the Lucy internships, if you get an offer, not just at NASA, but at any internships that you receive, we'd like to know about that. So
Yeah.
Feel free to email us and let us know where you were offered an internship, what you'll be doing, and we'd love to create some type of portfolio that Jessica's actually helping me put together.
That's right. And, you know, it's also getting yourself ready to take that step into internshiphood, if that's a word. But, you know, there's lots of opportunities, and even in your local area, I know in the Phoenix area, we have a lot of aerospace companies that work on NASA projects. So there's not just NASA, but there's NASA affiliates basically that can also be great ways to do it. You can also do internships, and having run NASA's internships, you might want to look at a semester internship and apply on the NASA internship site for a spring or fall. You have a lot less competition. It's a third longer in terms of the not 10 weeks, but you get 16 weeks or 15 weeks. And it is really an immersive experience, again, that they're always looking for people on the semesters as well. So anyway, Cavion. Hey, Cavion, the word's out, just so you know. Somebody's leaking it. Anyway, we've got a lot of great ideas going on within this project, and I know Jessica, I just saw an email from her, Jessica Thompson, who just spoke to us, and she's talking about the campaign, the viewing campaign, and she's going to get me the information for the Slack channel for all of you that are interested. So we'll post that on the Trello boards. So that should be good. And I think, is that all we had to cover tonight? Any last questions, La Spacers?
Oh, Sherry, I have an important one.
What's that?
Multiple times. Can students who are graduating this May participate in the level 2 session?
We are going to ask NASA that. Right now we were told undergrads, but maybe alumni we might be able to fold in. We're hoping to. So I'll give you that information right now. And as soon as we confirm that, again, we're talking with NASA on Monday. And as soon as we confirm that, we're hoping to go ahead and fold in the people that are going to be graduating this spring, that they can take it this summer. Okay?
And I have a question. Would you like to give a shout out to some of our ASU Lucy interns?
Oh, sure.
That are on here right now. Those that have confirmed.
Sure.
So Sherry and I were making some calls, and Jesse Arriaga is in the session. Congratulations, Jesse. You're one of our Lucy interns here at ASU. Joshua Bocanegra. Joshua, congratulations. Giovanni Cervantes. Giovanni. Christy Cummings was another one. And Elizabeth Jewett. So congratulations. They're in the actual session right now. So I wanted to make sure.
And those people answered their phone today, huh?
Yes. If you have a missed call from a 480 number,
it could be you.
You could be one of our interns.
Check your phone.
Any calls from Arizona that you missed today?
Yeah, not that we let the cat out of the bag there, Dan, but they all stopped talking because they're checking their phones.
Yes.
The chat just quit. No. Okay.
All righty.
All right. Well, Well, I think we've caused enough damage for tonight.
Yeah, I think so.
We really appreciate you working hard on your PDRs. Again, reach out to us. If there's not something you understand, if you're struggling with something, you will have your budget template very soon. I just need to have enough energy to stay awake till midnight to finish it. Oh, Marco, you did miss, you missed a phone call? We'll have to check the list. So anyway, we're going to be looking forward to working with y'all. We're looking forward to the PDRs. Have a good, safe weekend, and we look forward to seeing you next week. We've got a great speaker next week. I'm just looking at the schedule here. Where's my schedule? There it is. All right. So we have coming up. Oh yeah, we've got a spacecraft design session. That'll be great. So we've got great speakers all the way through the end. We're hoping you're not going to miss, because we've got fantastic times, you know, in real time, that you're going to be able to meet with these special speakers. So anyway, with that, I think we ought to say good night.
We shall. Good night, everyone.
Good night, and we look forward to seeing you next week. Let us know if there's something that you have on your mind, and we'd be glad to respond. All right. Good night, everybody.
Good night.
God is like a racist.
Have a good night, guys.
Good night, Jesse.
Good night.
Good night, Ghanem.
Yeah, because before it was like if you looked down, it would.
Good night to you.
They get louder the more they watch.
Good night, Trevor. Good night,
Like, they
Noel.
like speed up their aging.
Good night, Okita.
It's like all my grandparents watch, and they just
Man.
but it's